Okay, so this video is on calculating Kc or Kp using ice charts. So that is going to be when we have equilibrium data, but we also have some initial data. Okay, so we were working off of this worksheet. We saw the first two where they were very straightforward Kc, Kp situations where we were given all our data, and basically it was a plug and chug problem. Okay, so now we're on the third one down here. And if you read it, it says a closed system initially containing some H2 and some I2, and of course they give me the numbers, is allowed to react to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative 3 molar. Calculate Kc for this reaction. Okay, so here's my reaction. All gases, but they're telling me to calculate a Kc, so that's fine. Okay, so if I'm going to calculate a Kc, I'm going to jump over here and write my expression, which of course is my products over my reactants raised to their coefficients. Okay, so there's my Kc situation, and here, let me adjust the camera just a smidge. Hold on one second. Okay, so if I had those, if I had these numbers, I could just plug them into my Kc and solve the problem. Okay, however, if upon close examination of this problem, we've talked about this, that the numbers that go into Kc or Kp are equilibrium data, okay, because K is an equilibrium constant. So if you notice, in this situation, they give me info on H2, I2, and on HI, but only one of those numbers is an equilibrium concentration, and it's the product, because the first two have a keyword, and that keyword is initial, okay? Initial data cannot go into Kc or Kp. That is a huge takeaway, okay? No initial data in Kc or Kp, only equilibrium. So now the situation becomes, well, how do I find these concentrations? So if you're thinking about it, we know this number, okay, they told us what it was. It was 1.87 times 10 to the negative 3. I have to square that, okay? But that's the equilibrium concentration of HI. And so while that's fine, I don't know these two numbers. Okay, so we're going to solve this problem using something called an ice chart. And an ice chart is widely used in chemistry. So the way we use an ice chart is we write our reaction, and then we kind of draw a chart underneath the reaction, and we're going to label I, C, E down the side, okay? And this is why it's called an ice chart. I stands for initial, C stands for change, and E stands for equilibrium. So if you'd like to label that, you can. I'm not going to. I don't have enough room. There are some professors who might, and some teachers who might call this a rice chart, R for reaction, but the bigger name for these are rice chart. Our ice charts. Sorry, but you may hear a rice chart from your professor one day. Okay, so then what I do is I fill in the information that I have. So this problem says that I had an initial concentration of this as 1.000 times 10 to the negative third. Okay, so I filled it in under initial. And an initial concentration of I2, that was 2 times 10 to the negative third. Okay, and then the only number I know is my equilibrium concentration of HI, which was 1.87 times 10 to the negative third. Okay, now, what we're going to do is we're going to treat this kind of like a big math problem. All right, so first of all, if you think about this as a chemical reaction, if I have H2 and I2 in my container at time 0, how much HI do I have? And the answer to that is I have none, because the reaction hasn't happened yet. So my initial concentration of my product is 0. Okay. So then we're going to talk about the change line. So the change is going to be by how much are these reactants and products increasing or decreasing as equilibrium is approached. So the situation here is we have to think about who's increasing and who's decreasing. Well, there's only one way that this problem makes sense, and that is that these two are my reactants and they had to decrease, and this is my product and it had to increase. The other way to think about that is, I mentioned we're going to treat this like a math problem. So going from 0 up to this concentration, there's only one way to get there, and that is to add this amount. Okay, so my product increased while my two reactants decreased. So in an equilibrium situation, you're always going to have one side of your reaction increasing and one side of your reaction decreasing in the change column or the change row, okay? So now we play the game of, well, if I started with 0 and I ended up with this, how much did this change? And it's a pretty obvious answer in that this had to go up by this amount. Okay. And you might be thinking, well, how does that help me find these two? And it helps me find those two because from here on out, it's all related to stoichiometry. Okay, and so now I go to my ratios in my problem and say that, well, for every 2 HI that were formed, I was losing one of these and one of these, okay, which means I can relate stoichiometry to my change line. So if this number is representing how much HI increased, half of this number is going to represent how much I2 and H2 decreased. So if I take half of that on my calculator, I get this number. Okay, notice it's the same for each because their coefficients are the same, okay? So now I just do the math. It's like a big math problem. This number minus this number will give me my equilibrium concentration, and this number minus this number will give me my equilibrium concentration. Once I've done the math, I end up with something like this. Okay, and now I have my 3 equilibrium concentrations that I can now plug into here and solve for Kc. So now it's a matter of a plug and chug. Okay, so I would take the concentration of H2, which was, I'm not going to have enough room, but this guy, okay, and I'm going to multiply it by HI's concentration. Okay, and assuming I make no math errors and assuming I don't forget to square HI's concentration because that is a part of my equilibrium expression. Let me see, I did my math here, probably 3 sig figs, and I got 50.5 as my Kc value. Okay, so again, don't just trust me, you do the math and you check it, but I arrived at 50.5. So that's using an ice chart to solve a problem where we're not given all equilibrium data. We have one more, which is the back of your page, so let me erase the board and we'll solve that one. All right, so my second problem says sulfur trioxide decomposes at high temperature in a sealed container. And here's my reaction. Initially, the vessel is charged with SO3 at a partial pressure of 0.5 atm. At equilibrium, the SO3 partial pressure is 0.2 atm. Calculate the value of Kp. Okay, so again, I'm looking for a Kp. I'm going to write down here this time. Pardon my barking dog. I'm looking for a Kp, so it's probably smart for me to write the Kp expression. Of course, products over reactants raised to their coefficient, so partial pressure of SO2 squared times partial pressure of O2 over the partial pressure of SO3 squared. Okay, and again, I'm going to plug in my equilibrium partial pressures and I'll solve for Kp. However, that being said, I noticed right away that there's a giveaway word in this, and that is that they give me the word initial, okay? And so I shouldn't say always, but most of the time, if you see that word initial, you're probably going to need an ice chart, okay? So I know I'm going to need an ice chart. So I set it up under my reaction, ICE down the side, and I'm going to fill in everything that I know. So initially, my SO3 partial pressure was 0.5. And at equilibrium, my SO3 partial pressure was 0.2. So this time I'm given data on the same species. Okay, again, thinking about the fact that I'm going to treat this like a big math problem, I can kind of, I put my line there. All right, so it seems like we might not have enough data to solve this, but again, think about it. If in your flask you only have SO3, how much SO2 and O2 do you have initially? The answer to that is 0. And then I go into thinking about what's going to happen with my change. Well, these two have to increase, and this one has to decrease, right? Again, the only place I can go from 0 is up, and if my products are increasing, then my reactants have to decrease. But now the only question is by how much, okay? And it's pretty obvious if you look at it. How did I get from 0.5 to 0.2? Well, I had to lose 0.3, okay? And if this one lost 0.3, then I can use that to equate the other two using my stoichiometry. So again, I go to my reaction 2 to 2 to 1. So 0.3, this should be 0.3. And this should be half of 0.3 since 1 is half of 2. So this is only going to increase by 0.15. 0 plus 0.3 is 0.3. 0 plus 0.15 is 0.15. And now I have all three equilibrium partial pressures that I can put into my Kp expression. So my equilibrium partial pressure of SO2 is 0.3. Now I just have to be careful that I don't make a math error. I'm going to square it times partial pressure of O2, which is 0.15, divided by partial pressure of SO3 squared. And if I don't make a mistake and I do my math correctly, and again, I recommend you do this, I got a Kp of 0.338 as my final answer. So that's using ice charts. A couple notes about ice charts. There are only two pieces of information that can go in an ice chart. This is another huge takeaway. You can put partial pressures in an ice chart, and you can put molarity in an ice chart, and that is it. Partial pressures in an ice chart and molarity in an ice chart.